Assalamualaikum and good morning. So my group will be presenting about Riverworks and Canals. So this is my group members. Firstly, my name is Alisa, and then we have Muhammad Shahrul, Nur Hidayah, and Nurul Zatul. Riverworks are human interventions or engineering modifications made to the natural course or features of rivers. River restoration is important for reducing the risks associated with natural river dynamics like erosion, sedimentations, and seasonal flooding. Riverworks are also being implemented to improve navigations, while canals are man-made water channels that serve specific purposes.
So next I will explain the type of riverwork and channels. A river is a natural flowing watercourse which is usually fresh water flowing toward an ocean, sea, lake or another river. Rivers are sources of water needed for irrigation, water supply to town, industry, recreation and hydropower. So rivers are divided by three, which is river in hills, is known as upper reaches, river in alluvial plains, which is a lower reaches, and a tidal rivers. So a river division is the plain rerouting of water flow from its natural course or channel to an alternate path or channels. So typically this is accomplished by constructing structures or excavating channels to redirect the river's flow. So riverbank and protections mean preventing erosions and keeping a river or stream bank stable. So this is involve a building structure or using method to stop water from slowly wearing away the banks. So next is the designs of riverworks and channels. The design of riverwork and channel is an important part of water engineering. So it helps to control water flow, prevents flood, and improve navigations. So environmental considerations are also essential to ensure minimal disruption to aquatic ecosystem and riverine habitats. In urban setting, channel designs are often incorporate aesthetic features and recreational zones alongside flood control and mechanisms. So beside the main structure, riverwork and channel design must also plan for a long-term strength and flexibility. So the designs need to think about future climate changes like heavy rains and higher water level, which could affect the system durability. And also planting grass and shrubs on slope help prevent erosions and improve the environments. Features like access point, culverts, and bypass channels are added to make maintenance easier and more efficient. So next is the construction process. The process begins by identifying the purpose and functions of the rivers. A channel structure, along with the environmental considerations it will face such as a water flow, sediments, and a debris. Next is engineers determines the design flow keeping in mind that natural water levels may exceed predicted values and excess potential risk and a structural damage during extreme conditions. That one is the site is prepared by draining and clearing vegetations along the proposed channel alignments. Fourth is excavation is carried out using manual tools and machineries like shovels, carts, cranes, dredges, and scrapers to shape the canal routes. So the next step involves forming embankments and adjusting channel elevation through a series of level channels and constructing leaf locks for a broad passage between different heights. So locks are built using materials such as stone, timber, or cement, depending on local availability, to manage water flow and navigations. So engineers ensure there is an adequate and continuous water supply by identifying nearby sources, building reservoirs, dams, and digging feeders to maintain water level. Finally, structures like culverts and aqueducts are constructed to allow the channels to cross over rivers and streams with design made to withstand flooding and protect canals' integrity.
Next is materials. The first one is pedal clay, used to line canals and riverbeds because it efficiently reduces the seepage. Secondly, we have concrete, which is a popular lining material as technology advances because it strengthens the durability and hydraulic advantages. It is also generally produced using slip form processes, provides good impermeability and endurance, with thickness ranging from 5 to 15 cm depending on the structural needs. Thirdly is compacted clay or bentonite layers. It is to stiff the concrete that provide cost-effective permeability control and also can reduces the seepage and stabilizes groundwater. Lastly is rock and gravel, which is used in embankments and revetments, and also to prevent erosion. For false work, it is a temporary support structures used during the construction of hydraulic infrastructure, such as bridges, culverts, and spillways in canal and river projects. The traditional timber falsework is still used for smaller scale or distant operations because it is cheaper and also easy to handle. Next, steel systems have higher strength and reusability, making them excellent for larger lots in bridge piers, aqueduct superstructures, and also large canal crossings. The falsework must withstand not only static loads, such as wet concrete weight and formwork, but also dynamic forces. Lastly, for falsework, the modular systems or changeable falsework improve efficiency in areas with changing water levels, such as tidal or monsoon affected zones.
Next is the case study. Environmental Impact Assessment (EIA) in Sarawak is mandated by the Natural Resources and Environment Board for major projects such as hydropower dam, flood mitigation, and agriculture expansion. Its purpose is to evaluate potential impact on water quality, river hydrology, biodiversity, soil stability, and the livelihood of local communities. For example, the Lower Saribas project identified risks like soil erosion and recommended mitigation measures such as buffer zone and drainage control. However, the AIA process faces limitation. It often focuses narrowly on individual projects, overlooking cumulative impact like those from multiplied dam on the Rajang River. Additionally, community engagement has been inadequate, with indigenous rights and settlement sometimes being ignored. Sarawak River Basin Project Background. The Sarawak River Basin, located in Sarawak on Borneo Island, covers an area of about 2,459 square kilometers. Rapid urbanization has led to challenges such as water scarcity, pollution, and frequent flooding in the region. To address this issue, the government launched the Integrated River Basin Development Project, known as PLSB, with an investment of RM 191 million. This project aimed to improve flood mitigation, water management, and environment conservation, targeting completion by this year, 2025. The PLSB is part of a larger effort under Malaysia 11 Malaysia Plan, which include 22 flood mitigation projects across Sarawak with a total budget of RM 561 million, reflecting strong federal commitment and to tackle flood disaster and protect communities. The Department of Irrigation or and Drainage or DID Sarawak leads the Sarawak River Basin project. They work closely with several collaborators, including the federal government, which provide funding and policy support. Other key partners include the Department Environment, Sarawak River Board, and the Land Survey Department. Local council, non-governmental organization, and community group also play important roles in planning and conservation efforts. Next is construction technique. The project uses rock-filled weirs, RCC gravity dam, and the tidal barrage with ship block for water storage, flood control, and stopping saltwater intrusion. Urban drain and detention pond help manage flooding in Kuching. And for major project component, the key structure include the 25 submersible weirs securing Kuching water supply. Next is the 2000 Kuching barrage control water level and flood risks, and at the 2010 Bogor Dam providing long-term water supply storage and flood mitigation. And lastly, the Kuching waterways system treating pollution to protect river quality.
Starting with Bangor Dam, step 1, river diversion using a twin box culvert. 4 meter times 4.5 meter to redirect flow during construction. A third culvert was added later to protect upstream village. Step 2, main dam built with rolled compact concrete RCC with 160,000 meter cube placed with precise slope 0.78 to 1 upstream, 0.9 to 1 downstream for stability. And step 3, stepped spillway added to handle extreme floods with 2,420 meter cube per second flow and reduce erosion. For the Kuching Barrage, the 5 radial steel gates, each 2.5 meter wide and 168 tons, were installed to block the tidal surge. Gates open twice daily in a dry season to flush saline water downstream to protecting freshwater quality. Finally, the Kuching centralized water management system as a wastewater system use a trenchless technology, which is the tunnel boring machines TBMS, laid 64.4 kilometers of pipe, which is 6 to 27 meters underground, minimizing the urban disruption. Materials were chosen for durability and environmental resistance. For Bangor Dam, the RCC for seismic strength to plus with the stainless steel valve to resist the humidity and corrosion. Meanwhile, for Kuching Barrage, the precast concrete and steel gates to withstands the tidal forces and salt water. For Batu Kitang Ware, the Amarok from 0.6 to 1.4 meter diameter to stabilize the riverbed against the erosion. And for the KCWMS pipes, the HDPE plastic for flexibility and leak-proof seal to plus the reinforced concrete for treatment plants. Several critical issues arose during operation. For the first issue is the saline extrusion. The risk is the saltwater contaminating the Kuching freshwater supply. For this solution, the barrage gets regulated tides, which is to the maintaining a permanent freshwater reserve upstream. The second issue is the sedimentation. The risk here is the worst of clogged channels, reducing the water flow. The solution is the weekly flushing of barrage gates to, to add on with the periodic dredging. The third issue is the low dissolved oxygen or DO. The risk is the polluted wastewater killing aquatic life, and the DO dropped to 0.5 mg per L. So the solution here is the KCWMS wastewater to standard equality, which is to raising a DO to 4.0 mg per L. And the last issue is urban flooding. The risk here is heavy rains overwhelming the Kuching drainage. So the solution is the Burger Dam spillway diverted the floodwaters and plus with the barrage gates control the water level.
For conclusion, water resource management, urban flood control, irrigation, navigation, and also environmental sustainability all rely heavily on the river and canal works. The Klang River is a local example of how rivers and canal systems may affect their urban environments. Riverworks and canals are more than just practical hydraulic constructions, but they are critical to the sustainability, safety, and livability of urban and rural communities. Lastly, the Klang River experience demonstrates the significance of integrating engineering knowledge, environmental awareness, and also public participation. Thank you.